Hi everyone, and welcome to today's webinar, Driving Research to New Heights, Wearable Eye Tracking, and Automotive Simulators. My name is Keith Bartels. I'm the West Coast Account Manager on the Market Research and User Experience team here at Tobii Pro North America. Today is a very exciting webinar because joining me is Christian Roth. He's the CEO of FKA Silicon Valley. In terms of the agenda for today's presentation, we'll start with a high-level look at the two companies, Tobii Pro and FKA. We'll then look at a zoomed-out view of eye tracking, high-level overview of what is it and how does it work. We'll then switch to Christian's section, where he's going to explain his experience with the Tobii eye tracking glasses, as well as detail a couple really interesting case studies. And at the end, we'll have a much longer Q&A as well. Looking at Tobii Pro, we are the global leader in eye tracking research and technology, headquartered in Stockholm, Sweden, with offices all across the world. At Tobii Pro, we have an extensive portfolio of eye tracking hardware, software, and research services. We also have some great packages designed around customer success with some very helpful training elements. Because we view ourselves as much more than just an eye tracking vendor, we are much more your research partner. So we are happy to customize our offering to fit any specific research goals that you have and ensure a successful eye tracking experience. Looking to FKA, this company was founded in 1981 as a spinoff from the Institute of Automotive Engineering. FKA offers very advanced research solutions for both public as well as private research projects. They founded FKA Silicon Valley in 2015 to meet the rapidly growing automotive ecosystem in Silicon Valley, as well as to service the rest of the North America market. And to expand more on FKA and FKA Silicon Valley, the offering, this chart here just shows that they can support literally every aspect of the automotive development process with the exception of combustion engines. So as you can see, things like user experience, vehicle concepts, electronics, thermal management, much like Tobii Pro, FKA can be flexible and work with you to make sure your research and project is successful. Now let's take a look at eye tracking. What is it and how does it work? Throughout our day, we make thousands of decisions, many of them unconsciously, and it's often difficult to recall or talk about what we were thinking as we made those decisions. Eye tracking can help to solve that problem by giving you an objective capture of user experience in almost any situation imaginable. Especially when we talk about a wearable eye tracking, where you have the eye tracker and sensors built into a set of glasses. It's an extremely versatile solution because the person can be walking down the streets, looking at their smartphone, going from screen to screen, driving in a car, and you as the researcher, you're going to be right there via the eye tracking glasses to see the accurate and precise measurements of their attention. On this next slide, I have a nice video that I prepared that kind of puts this all together with a couple of different automotive examples, all featuring drivers wearing Tobii Pro glasses. Let's take a look. So as you can see here, this red circle in each of these clips represents the attention of the driver. So the driver is wearing Tobii Pro glasses, and this just helps demonstrate, especially in these vehicles today where we have all these different screens and buttons and various controls. It's so complicated that having a way to measure the attention and monitor things like driver distraction, usability of the new navigation system. If we're talking about an autonomous car like the Tesla you see here, is the large screen in the center dash, is it creating an unsafe situation where the eyes are going off the windshield for an extended period of time? Or is the driver is entering their coordinates or setting up their sound system? Was the experience smooth, or were there a couple issues along the way? This is where the eye tracking can really help tell that true and full story of the driver experience, indoors, outdoors, on a bright day or at dusk, or an automotive simulator. So it's a very powerful way to take that automotive research to that next step. Now let's take a look at the full offerings in terms of eye tracking solutions from Tobii Pro. So on the left, you can see we have high fidelity eye trackers like our Tobii Pro Spectrum. Moving to the right, we have very portable remote eye trackers such as the Tobii Pro Nano and Tobii Pro Fusion. We have our wearable Tobii Pro Glasses 3 that we'll expand upon in just a moment. And we also have our webcam platform. It's called Sticky by Tobii Pro. So it's good to remember we have this because if you can't do in-person research with our Sticky platform, you can actually utilize the built-in webcam on a participant's laptop or desktop screen and track and analyze their attention via that built-in camera. So quite a portfolio we have at Tobii Pro. Let's expand more on Tobii Pro Glasses 3, the star of today's presentation. This is the full solution that you see here. So the Glasses 3 has a headset with built-in sensors that connects down to a small recording unit. There's a belt clip on the back of the recording unit, so you can easily clip it onto your pocket or hip, put on the glasses headset, and then go right into your task or experiment. Getting into more detail on the headset, I just want to go over a couple of these key capabilities of the wearable. The Glasses 3 does feature a built-in microphone, so if you're doing a driving test, for example, it's going to pick up any kind of narration or commentary throughout the test. So as the driver is experiencing some sort of new in-car interface, for example, and there's an issue and they are having trouble with it, they might be voicing some frustration, you're going to capture that as well as the eye tracking and the video. The sensors themselves with Tobii Pro Glasses, they're actually molded into the glass itself. That's a world's first for a wearable. So there is a series of IR illuminators built into the left and the right side, and 2 eye tracking sensors per eye as well, again, all molded into the glass. The headset features an adjustable nose piece, so you can actually swap that out for different included sizes. So you can have a comfortable fit for drivers who might have smaller or wider nose bridges. And the front-facing camera is going to capture a nice HD view inside the car or anywhere you want to test, capturing a 160-degree field of view. Looking at the software side of things, there's 2 routes you can go with Tobii Pro Glasses. We'll start with the Tobii Pro Lab software first. This video here on the right just is demonstrating a couple of the key features. So we have advanced algorithms that can help with automating the data mapping process. You can create powerful visualizations like you see here. So you can look at a plot of every spot the driver looked or a heat map to identify at a high level where those clusters of attention occurred. Or if you want to go even more into detail, you can use our areas of interest tool and outline any screen or button or windshield in the car. And from those defined areas, you can then export detailed metrics such as time to first fixation, total duration of fixation, visit count. Again, you can get that really detailed story behind how the driver experienced whichever car interior you're testing. On the other side of things, we have an API for Pro Glasses 3. It's platform and language independence, and this is a great fit if you want to sync the raw gaze coordinate feeds into an existing setup you have. So if you did have an automotive simulator, like Christian's going to talk about in just a moment, you could actually use the API to code and build your own application to feed in the eye tracking and thus add that tool to the overall setup. We have a webinar that I'm happy to share the link on after the presentation. It's over an hour long and it goes into all the details on the API and functionalities. So I'll definitely share that after the presentation. And now let's get to the special guest for today's webinar, Christian Roth, CEO of FKA Silicon Valley. Christian's going to speak about his experience with eye tracking, talk more about the company as a whole, detail their state-of-the-art automotive simulator, and talk about those case studies. So Christian, take it away.
Thank you, Keith, very much for that nice introduction and a quick intro into what FK is and what we do and how we work. For everyone else in the audience, if you have any more questions about FKA and what we do, how to interact with us, feel absolutely free to shoot me a message after the webinar or ask any questions in the Q&A, as Keith mentioned. Now, Keith spoke a lot about what eye tracking is and how to use it in general terms. I want to specifically talk today about how to use eye tracking in driving simulators because that's one big field of work for us. And to do that, I want to cover some of the basics about driving simulators in the beginning. Now, the first question you might ask is why use driving simulators in the first place? Well, there's a lot of benefits to it. Comparing it to testing on test tracks or on open public roads, first and foremost, it's a very low risk environment, which means we have a very controlled surrounding and there isn't much that can go wrong. The maximum is maybe a little bit of motion sickness that can come from the lack of G-forces in the simulation. But other than that, there really isn't many risks involved. But we still get a very high level of immersion. It feels very realistic to the participant, and so people behave in the simulator just the way they would on the actual road. Another big benefit is because we can control the entire simulation, it means we can exactly reproduce every scenario that a participant will see in our simulator. That can be very important if we want to see, for example, if someone recognizes that there is a pedestrian, let's say. We need to make sure that that pedestrian is in the same spot for every person we test to make actual conclusions from that. And in the driving simulator, that is very simple for us. We can program it. Now, we can not only program it to occur at the same time, but we also have a very comprehensive set of knowledge about this simulation. We have all the data we need, and we can completely record all of that data, which means we can analyze it in the most accurate way. Apart from that, there's many benefits, and I'm going to cover just a couple here, and I don't want to sway way too far, but another benefit is the integration of external devices. We have a vehicle that doesn't actually have to drive, which means we can create extra spaces, we can mount things in places that might not be possible in actual real-world driving. And so we have a very easy time to integrate all kinds of external devices. Now, with the eye tracking devices we talk about today, that's not so much an issue, but let's imagine you have a very large biometric scanner or some type of device that is pretty large. Maybe you don't get that into an actual vehicle. Well, in the driving simulator, that's really not an issue for us. And that leads us to customizability and flexibility. Our simulators are quite flexible. We can modify the vehicles to any of our customers' needs without having to worry about driving codes and safety issues. And then lastly, that also kind of comes in that same field, we can test things that are very early stage in their development. Maybe you haven't validated them. Maybe you don't feel confident to put that out in the road yet. Maybe it's even about confidentiality. You don't want anyone to see it. Now, in the driving simulator, we can test all these things very easily. And lastly, well, driving simulators are a very accepted tool in validation. They're included in guidelines, and that means it's not just us using them, but it's the entire industry. So why use them? Well, because they're actually quite a validated and accepted tool. And for everyone who might not have seen the driving simulator, I brought a little video just really quick to give you an idea of what our simulator looks like. So as you can see here, the surrounding is moving, but the vehicle is completely stationary. But at the same time, you really create the immersion of driving. And you have the sound, as you can hear. It's really quite a unique experience if you have never tried it. We talked about why using simulators, but what are they used for? Well, a lot of what we do is driver behavior analysis. This includes anything from how do people drive on a regular basis, how do people drive when they're under the influence of medication or drugs or certain emotions like stress and anger. We can test those things, again, very safely because even an enraged driver might not be able to harm anyone else in a simulator. We look at a lot of user interaction, which means, for example, how do I interact with my vehicle, but also how do I interact with other agents on the road? One big topic here might be automated vehicles, where you look at do people drive differently when they see an automated vehicle that does not have a driver in it in the car. Then there's human-machine interfaces, which are a big topic. We look at usability and acceptance. We also look at distraction from these interfaces, and they can be quite complex. It can be anything from the steering wheel, where, for example, we've tested side sticks instead of a steering wheel to control the lateral motion of the vehicle. This can be infotainment systems and anything really where the human interacts with the machine. Another big area that we look at are driver assistance systems. those systems are quite complex, and sometimes it makes sense to test them in a simulator first because some of the components of that system might not be fully developed yet. I'm thinking about sensors, for example. If the sensor itself doesn't exist yet in the simulator, we can pretend to have that simulator and give the system the output that the sensor would create, and by that enable us to test that driver assistance system already, even though some of the components don't exist yet. And then another very, very big area that we use the simulator for is automotive guideline testing. So guidelines might be put out by NHTSA or other bodies that have come up with a standard for best practice testing of devices and systems inside the car. And simulators are usually one of the highest fidelity ways of testing this. And so that is a big field for us to work with our clients in. And lastly, we like to think of the driving simulators as time machines because they allow us to test future concepts prior to their validation. I've talked a lot about the low risk factor of simulators, and this really relates to this. If you have something that might not be fully developed, might not yet be safe for testing on the road, you can bring actual participants into the car in our simulator and show them what it would feel like and get first impressions. Would they accept it? Would they want to use it? Is it intuitive? You can get these things in a very early stage, maybe even about things that people can't imagine yet. And obviously, if we use a simulator as a scientific tool to validate systems, we need to measure data. Now, we have a lot of ways of measuring data, one of which is subjective data. Subjective data can be quite simply collected in the simulator because we have very little logistics involved. We can get a person into the car and into a different room quite quickly. It's not that different from anything else, really. We use the same type of customized or standardized questionnaires here. Really depends on what our clients need. Now, performance data, that's a very interesting one because, as I mentioned, we have a comprehensive understanding of our surrounding, which means we actually have all the data we want. We just need to make sure we record it correctly, we make sure it's synchronized, and then we have the most comprehensive performance data set we can imagine. And then additional metrics, I've talked about that a little bit as well, because we have the flexibility to integrate external devices into our simulator quite easily. That means we can get a lot of data on the physiology of our participants, and especially eye tracking in this case is what I want to talk about today. Now, eye tracking in the driving simulator comes basically down to two choices. The first choice is mounting the eye tracking cameras onto the dashboard. That's one way of doing it, and it has a couple of benefits and disadvantages. The benefit, it's a user-independent system. It's in the car, and you don't have to have the participant interact with it in any way. It has a fixed position, which means it doesn't move around, and it's right where you expect it to be. And it gives you 3D gaze positioning. Because you use multiple cameras, you can pretty much dial down the gaze of where it is inside the cabin in a 3D manner. Now, the disadvantage of such a system, you have the possibility of obstruction. A participant who steers the steering wheel might obstruct one or two cameras with their arm, and then you don't have gaze data for that moment. Maybe you just have one camera and your gaze data isn't quite valid. The adaptation and calibration is a bit of a disadvantage because every participant is slightly different, sits in a different position. You need to make sure that the cameras always point at the exact right position of that participant. So there's a little effort involved in calibrating these systems and adapting them to every participant. Another disadvantage, well, they're cameras, they're visible. And people who get into a car and see cameras might react a little differently, or you have to give them more time to get used to it. And then it's a multi-device setup, which means there's more components that could go wrong. There's more things that need to be synchronized. Overall, that just adds complexity to an already very complex environment. The other way of doing this eye tracking in simulators is face-mounted devices, just like the Tobii Pro glasses that we're talking here about today. Their advantage, there's no obstructions. Even if my hands are on the steering wheel, I can see my full gaze at all times because the cameras are really close to my eyes. There's no integration. what I mean by that is we don't actually have to install the eye tracker into the vehicle. In some cases, maybe we have a customer vehicle that we put into our simulator, and we're not actually allowed to modify the interior in any way. And then we have to be quite creative to install a dashboard mounted system. But the face mounted system doesn't have that issue. And in the same way, it's mobile. That means we can, for example, monitor the process of getting into the vehicle as well. With the dashboard mounted system, we don't have those abilities. We get a live field of view, so we can at all times completely capture what the participant is seeing, including their head movements. And with dashboard mounted systems, most of the time we have a static scene camera, so we don't get that exact field of view. And the calibration process is quite quick with these face mounted systems. The downsides, of course, they have some as well. We have limited storage. In this case, we're using SD cards and they are limited. So depending on how long our test is, we have to make sure we allow for enough storage. The same goes for battery. A mobile system always runs on a battery. There is ways to connect the Tobii Glasses recording units to a power source, but these are just considerations you need to make depending on your study. And of course, it's a user-bound device, which means participants have to put it on, and that can create some uncomfort in some cases. But generally speaking, they're just very regular glasses, and they don't feel much different to wearing sunshades, for example. Okay, now that we've covered the basics of eye tracking and driving simulators, I want to get into some of the example use cases that we have and how we use the simulators to actually test visual load. And we refer to these as secondary tasks because the primary task is always the driving task, and the secondary task is any type of device or system that you introduce and ask the participant to interact with on top of what they're already doing for the driving. Now, the first example task that I brought is the NHTSA radio tuning reference task. It's a task described in NHTSA's guidelines for visual manual driver distraction. And it's a pretty simple task. It basically is the task of changing the radio station from one preset to another by turning a knob or shifting a lever, something you can pretty much do in any car. Now, NHTSA's argumentation is that this task will introduce a level of visual distraction that no other task that you introduce into the vehicle should exceed. And it basically does this by looking against two areas of interest. The first area of interest is the forward road view. That's where a driver should normally be looking kind of straight ahead through the windscreen. And the other area of interest is everything else. I've loosely defined it here in the snapshot. As you can see, we have here the forward road view just fenced off pretty easily. And then we see the non-forward road view, which is kind of everything below. Now, the benefits of this task, it's actually a very simple example task. You can test it in pretty much any vehicle because every car that has a radio automatically has the ability to test this task. And it's very comparable, especially as a baseline test because you can create it in so many vehicles. Now, the limitation of it is it doesn't really distinguish the reason why a participant's gaze is not on the forward road view. So that may include me looking at my instrument cluster, my speedometer, that is just the same way considered a non-forward road view as it would be the glance onto my cell phone as I'm texting or as I'm looking at my infotainment screen. And I've brought a little video to illustrate what the radio tuning task will look like. The first one I will show looks from the perspective of a scene cam, kind of similar to what you would have with the dashboard mounted system, where you would just get a general idea, kind of a steady video of what it looks like. And then the second video will be the actual field of view of a participant interacting with the eye tracking glasses, with the Tobii Glasses 3. Now here we can see our simulator on the inside, driving on the highway, and then we see the participant starts interacting with the radio system, changing and putting the hands back on the steering wheel. Doesn't look very distracting in a visual way if we just look at it like this. But now if we take a look at it with the eye tracking glasses, and we'll have an overlay of the actual gaze of the participant here, we can see how much gaze diversion we actually see. So we can see there's some head movement going on. The participant is actually tilting their head. We can now actually see that we had a little bit of a lane exceedance here on the left that was corrected. And I'm going to play this just again one more time so you can see it again. There's actually quite a lot of glances happening. And that's really why NHTSA has defined this task as a good example and as a good baseline for what visual distraction should be. Another task that I wanted to introduce today is the surrogate reference task. Now, this is even more than the radio tuning task, a very high visual load task. It's defined by an ISO norm, and it represents a high visual demand because you basically have a picture here in which there's a lot of circles, and you have to find the circle that is different in size. Now, in this example, you probably have found it already. It's right here, but it's quite difficult. And imagine doing this while driving. It becomes even more difficult. That white line that you see in the image isn't an indicator of where that circle is, but that's the selector that a participant can actually move from left to right and then to indicate if they have actually found that circle. And on top of that, there's two levels of difficulty. There's a simple and then there's a difficult version. We are looking here at that difficult version. It is a widely accepted task as well. It isn't defined by NHTSA itself, but it's in the ISO standard and it is used in a lot of academic research. For those here in the United States, for example, David Strayer from the University of Utah frequently uses this method, and we use it quite often in our studies as well. And again, I've brought two quick videos to show you what these tasks look like, both again from those two perspectives as before. Quickly, the benefits and limitations of this task. The benefit is a very simple and high visual workload task. It's very comparable and easy to implement. However, the integration isn't trivial. So you either have to be able to integrate this into your dashboard display, and you also have to have the correct controls in the vehicle. In some cases, you may be able to use a tablet, but it's certainly not a trivial thing. And then another limitation that we originally didn't anticipate, but we have encountered participants who have a fear of holes, and the circles in front of that black background can actually, in some cases, create a bit of a phobia for some participants who then feel uncomfortable interacting with this task, and then you have to actually abort the testing there and get other participants in. So that's just something to remember, maybe something that wouldn't immediately come to mind. And here we see, again, from that reverse perspective, what that SURT task looks like. We can see here, that's actually myself. I have to take quite a few glances at the screen before I can even identify the circle that is different in size. And once I actually find it, I start moving that bar across and selecting that area. And if you take a look up here in the mirror, you can also see how many glances are diverted. But again, that isn't the greatest perspective to really see the visual impact. And so if we now go into that perspective from the eye tracking glasses again, you can see this is a different video in this case, but you can see how long the fixations onto that screen actually occur. And if we think we're now driving at highway speeds, we're traveling actually quite a lot of distance while we're executing this task. And so I just wanted to show with this why this is a high load task, why we use this as a high referent. And yes, we can really see how much visual distraction is happening there. Now, these two tasks are reference tasks that you use to test against your system, but then you obviously also want to test your own system or your own devices. And there's a couple of things to consider. Generally speaking, eye tracking is most suitable for visual manual interactions, meaning anything where you have to look and physically move or adjust things. But you can also test voice control systems, for example, because visual indications or visual data can be an indication of cognitive load as well. There's literature out there that shows that people that are very mentally engaged or cognitively loaded, they will actually have a phenomenon that's called looking without seeing. So they will have a very staring sort of gaze straight ahead, and they don't actually realize that they're looking at something because their brain is completely occupied with that mental load. In those cases, you can either track that staring gaze, or you can try and place objects and later on with subjective questionnaires question if they saw these objects, and if they say they didn't see them, but you have the eye tracking data that shows that we're looking right at it, then you have quite a good indication of that they were cognitively quite involved in that situation. And what I like to stress always, the most important step in such studies is the study planning. So answering the question, what is the goal and what is my research question? Having those two questions in mind when you design a driving simulator study with eye tracking is sort of the first step to set you up for success. And this is really, really important. And if you do that right, then you can use the eye tracking data really to its fullest extent. Okay, and now that we've covered what the simulator is and how to use eye tracking in the simulator and talked about some of the tasks that you can use and some of the benchmarks, I would like to give you some of the lessons learned that we've had over the time that we've had in using the Tobii Pro Glasses 2 and now the Glasses 3 as well in our simulator. The first one is being really sure if you want to use a filter or raw data. I brought a little video here to illustrate this, where we can see on the left side we have the Tobii Pro IVT filter. On the right side we see a raw overlay onto a video. Now the difference being here that on the left side we're seeing fixations only, on the right side we're seeing raw gaze data for every single frame where it's recorded. In some cases it can be just enough to look at the fixations, where it's really good to have this filter. It can speed up your data processing, and maybe you're just interested in sort of the general idea of where are people looking, where are they fixating themselves on. When you get into actual analysis of data and you need very accurate data up to like milliseconds, then using the raw data can be more the correct route, or you can use a combination of both. And with this video I just wanted to show you what the difference can look like. Now this becomes especially interesting when we look at the gaze mapping. Tobii Pro actually enables you, after you've recorded the video, to go into their software and map the field of view image from the video onto a static screenshot that you can create for your specific environment. And I'm going to talk about those screenshots in a minute. But this automated mapping should only be used as a baseline, because obviously it isn't perfect and it makes mistakes, or in some cases it can't detect. Especially in the driving context, we found that the quick head movements can be very challenging for the algorithm, because the image becomes a little bit blurry. And some participants, more so than others, tend to move their head quite a lot, especially if you're looking at infotainment interaction where people move their gaze down towards the systems. Now you can use the IVT filtered gazes fixations to control the automated mapping, or you can go through at the raw data rate, actually frame per frame. In some cases, the IVT filter method may just be perfectly fine. It's certainly quicker, but gives you a bit of a lower accuracy. We typically go through it frame by frame and then manually post-process the data again to make sure that we have everything correct. But there's a couple of things you can do to already speed up that process, even if you go down the raw data route. And that is your snapshot selection. Here we see on the left side the actual field of view image from the Tobii Pro Glasses 3. And then on the right here we have a snapshot that we took of our simulator, which is actually a good snapshot, because we can see the automated mapping from here to here is actually quite accurate. And one reason for that is because that's a good snapshot. Now I want to show you a couple of not so good examples. This example is not as accurate, and to basically, from our lessons learned, what we assume here is happening with the algorithm is that that picture is just not illuminated enough. So you can see that a lot of the features in the car here are quite dark, and that makes it more difficult for the algorithm to place that gaze exactly onto that screenshot where it is. Now, if we're only looking at forward road view, non-forward road view in the NHTSA case, that might not be a problem, but generally speaking, we want to have the most accurate data possible. In another example here, we also have a relatively dark snapshot, but we can also see that the perspective is a little bit different, and that change in perspective all of a sudden moves that point further to the left, because in our perspective, this moves further to the left, but for the algorithm, it's still just in front of that steering wheel. And so this is probably where it comes from. And our lessons learned here really is make sure you capture the snapshot from the same perspective that you would see with the actual glasses. And then just to illustrate that a little bit more, here we can see that perspective moved over a little bit further, and then we can see that it looks like that participant would be looking here at that side barrier or even off the road, while actually in the field of view we can see he's kind of looking straight ahead. And so we really want to make sure that the snapshot is selected correctly so that we don't have to go in and manually edit some of that data. Now, after we've mapped the data onto a snapshot, there's other steps in the data processing that we can do to make sure we have good quality data. Now, the Tobii Pro Lab software actually gives you a valid gaze sample rate for each recording. So just as you import it into the software, it gives you a little percentage indication of for how many frames it actually collected valid gaze data. You can also then later on use IVT filter to classify your eye movements into saccades and fixations, and export that data and kind of get your own estimates out of that, looking at specific times of interest. You can also use the raw data where Tobii provides gaze sample validity that can be exported per frame. What we typically do, we do a bit of a combined approach. We look at the IVT classifications for saccades and for fixations, and then on top of that we look at the actual validity rate for each of the eyes for each frame, and then compute our own calculations based on this. And then here on the right we just see from the ISO 15072 norm how ISO classifies data in terms of valid frames. So anything above 95% is excellent, anything about 85% is good, and if you're just above 70%, it's poor data, but it's still kind of acceptable. We typically, with the Tobii 3 glasses, end up well above 85% actually. And if we now take this example of the NHTSA guidelines and look at how we use data there and how we post-process the data coming out of the Tobii software, there is immediately one issue, and that's NHTSA only describes the handling of fixations. So up here on the top right, we look at that forward road view, non-forward road view decision or this criteria that NHTSA established, and there's no room for fixations. They basically say one fixation ends and the next one begins. And so what you can do is take the approach from the ISO norm again and fuse those fixations and saccades together. That is something that we do in the post-processing based on the data that we get out of the Tobii IVT filter, for example. And in some cases, maybe you want to define your own filter. Tobii allows you to do that as well, which we think is great because the IVT filter might not always be applicable. But our approach comes with a bit of a caveat. You actually have to have a very high level of synchronization, and especially if you look at multi-device testing. So on the bottom right here, we see an image where you can see all these little markers in our timestamp diagram there, and each of these markers represents an individual system that shows there's an interaction happening, or that is a time frame that we're looking at. And so we need to make sure that each of these markers is being synchronized to the same timestamp. And that's really a crucial step. And luckily, Tobii also gives us a little bit of a tool here that we can use. Namely, they give us a TTL port. And we can use this port to synchronize everything that the Tobii Pro Glasses record and synchronize it to our simulation environment. So in the end, we want to end up with one timestamp for every device. Now, the TTL communication from the recording unit to the computer can be done directly through the Tobii software, and that's a great way of using it if you really just have that one-way communication where the recorder basically sends out pulses and you can really just synchronize it back to this. Our approach, again, is a little more complex because we have a lot of experience with our driving simulator, and we've had just a lot of complexity in the system already once we introduced the Tobii Glasses into it as well. And what we do, we use the port in the opposite direction, and we send detectable pulses in a randomized fashion to the device, store them directly on the recording unit, and by that we're able to actually identify these timestamps based on that on those random stimuli in that situation. That obviously then requires a couple of more backend protocols that we have in place and some additional post-processing, but because we do run all of our data through a post-processing pipeline in the end anyway, that's not a problem. And what's really good for us is that Tobii has thought about this when they designed the system and gave us an option to actually interface this. Now, that being said, there's obviously more features that have been added with the new glasses that we haven't completely adapted yet to, and maybe we'll change this in the future, but just to say this already, coming from the Glasses 2, this was a great way for us to interact with this. And with that, that's sort of my quick wrap-up of how we use the Tobii 3 glasses currently, how we use eye tracking in general in the driving simulator, and what kind of little challenges and tricks you can expect to be working with. Obviously, we're very interested in working with anyone who might require our help or who wants to set up a system in their own lab. So if you have any questions that won't be answered in this webinar or in the QA session following this, feel absolutely free to reach out to me. I'll be happy to answer any questions and see if we can come together and work. And with that, I would like to turn it over to the questions.
Thank you so much, Christian, for that fascinating section. All great information. So before we hop into the Q&A session, I do have two quick polls, just so we can learn a bit more about the research of those of you in attendance. Let me launch the first poll now. So you'll see it pop up on your screen in just a second. So have you ever used eye tracking in your research? Yes or not yet? Looks like about 25% have voted so far, and I'll share the results as soon as we have a good sample. All right, so it looks like 84% of you are currently using eye tracking in your research, 16% not yet. And now for our second poll, what is your primary research focus? Driver UX, so usability of in-car technology, driver safety, driver performance, distraction research, or other. And if you do answer other, feel free to tell us in the chat specifically what that other research is. Responses are coming in. All right, let's take a look at the results. Looks like the majority driver UX, usability of in-car technology, 43%, 25% testing with driver safety, 7% driver performance, 11% distraction research, and 14% are other. So thank you for your participation there with those polls, and let's go ahead and hop into the Q&A portion of our presentation. Like the first question we have is from Steve. What is the battery life of Pro Glasses 3? So in terms of the battery on the glasses, it does come with 3 rechargeable batteries, each of which will give you roughly 90 minutes of recording time. There's also an included wall plug with the glasses kit. So if you do have access to an AC outlet, you can plug in the glasses and then have essentially unlimited battery power. Next question is for Christian from Josh. Why are you using a static simulator and not one that simulates motion?
Yeah, I think that's a good question. There's a couple of reasons for it. One big reason obviously is cost. So a lot of our customers, they test, as we've seen in the poll here as well, they look for usability and sort of the user experience of the in-car systems. And when you have someone interact with those systems in a static simulator, you already have that deep immersion, and you typically don't even test in very dynamic scenarios. So the track you would be driving on is typically very simple, a lot of times a straight road or a loop track. And so having the dynamic system doesn't actually give you a lot of benefits in terms of the results of what you get from the participants. However, it adds a lot of complexity and safety concerns. And so for those use cases, it just doesn't make a lot of sense, and it would be a lot more expensive to test in. And that's why the static simulator is such a good compromise, because it gives you that high immersiveness and a good quality of results, but you kind of keep the cost down for the client.
Next question is for you as well, Christian. It's from Sarah Maya. How frequently do you use eye tracking in participant studies in your simulator?
I would say most of them, actually. There's some cases where you're really just interested in the subjective feedback, and you're not necessarily interested in the visual features so much. But specifically for the guideline testing, where eye tracking metrics are one of the key criteria, we actually do use them in any study. Well, we have to because they're part of the guidelines. And so I'd say probably somewhere between 70 and 80% of the studies we execute recently do involve eye tracking.
This next question is for me. It's from Mary. I've seen a wireless version of glasses on the websites and mentioned in past presentations. Does this mean the headset doesn't need to be cabled to the recording units? It's a good question, Mary. So with Glasses 3, there are 2 versions. There's a wired as well as a wireless version of the hardware. But in either case, that headset for the glasses, it does have to maintain that cabled connection to the recording unit, so that HDMI cable. It's just with the wireless version, what we mean by that is that version actually pushes out its own Wi-Fi signal, enables you as the researcher to watch that live eye tracking or access those raw gaze coordinates in real time without a physical Ethernet cable between the glasses and the computer. But in either case, in terms of the connection, you do have to have that headset wired down to the recording units.
Yeah, and maybe, Keith, if you don't mind if I chip in, we actually, in our simulator, we would have the capability, because the car is stationary, to run an Ethernet cable into the car and connect the unit itself. But we actually like the fact that it's wireless, because we can clip it onto the participant before they get into the vehicle and then never worry about it again. So we still use that wireless feature, even though we wouldn't technically need it, but it's actually a good added benefit, because you put it on the participant before you instruct them on the car. By the time they've put the seatbelt on, they've done everything, they forgot that they've got the eye tracker on. So that's a good benefit for us.
Yeah, that's great feedback. Thanks, Christian. Next question is for you, Christian. Comes from Helena. What is your experience with users' feelings with car simulators? By that I mean car sick.
Car sickness?
So I'm guessing kind of that swimming car sick feeling you can get from some simulators.
Yeah, so absolutely. In a static environment where you lack the g-forces of both the turns and especially the deceleration, the braking, some participants get motion sickness. I'd say we get less than 10% though. There's a couple of things you can do, trying to keep the room temperature a little bit lower than usual, having a little bit of airflow going. Those are two very easy measures to kind of combat that. And then the driving scenario itself is a huge impact. So anything that's very dynamic, where the lack of these g-forces becomes apparent to the participant, or let's say subconsciously is apparent, they're obviously more prone to produce those motion sickness feelings. And we usually use tracks and scenarios that just don't involve this. We do operate a couple of warm-up drives to get people accustomed to the system before we introduce secondary systems and overload them, or put extra workload on them, and so that helps a little bit as well. But yeah, generally, if you control the track and the room temperature, you can get that to less than 10%.
This next question is from Chris. Is there an option for GPS with the glasses? So Chris, there's not a direct GPS feature with Pro Glasses 3. There's also not, in case what you mean is a heads-up GPS or navigation with the glasses lenses. There's no heads-up display or AR elements, but you can always use a third-party GPS if you must have that kind of information for your testing. Next question comes from Rachel. This is a longer one for you, Christian. Can you provide an example of how someone would use the reference studies? For example, would you bring in a participant, have them complete both reference tasks, then have them complete the customized scenarios, and then determine if your scenario results in low, medium, or high time away from the non-forward road view?
Yeah, that's a great question. So the two reference tasks I showed, they're a little bit different. The NHTSA radio tuning task is a pretty standard task that just says basically you don't want to exceed this level of visual distraction that you might experience from this task. So you could one-to-one basically benchmark your system against this one and say our visual distraction in terms of gazes off the forward road view is lower than the manual radio tuning task, and by that we feel confident that the visual distraction level is low. With the SURT, it's a little different. There's a couple of ways you can include this, and I mentioned David Strayer. He, for example, uses the SURT to create a standardized score. Basically, he uses 4 different components, which include task duration and then the visual distraction level measured by the system, and he benchmarks this against whatever the participant scores for the SURT task, and by that he can standardize the score for the visual component. And then he does the same thing for cognitive workload. He uses, like I said, the time duration of the task. And by that, he can combine a score, a complete score for a system. And with that, you can compare these systems because you have a score where you can say my BMW infotainment system, I can directly compare to that Mercedes system. And that's just one way. Another way would certainly to compare against it as a high visual benchmark. But then you really just have to make sure that the only distraction level you want to look at is the visual. And in most cases, you also want to look at cognitive workload and potential other things. So you might have to see if using just the SURT task is really good enough as a benchmark system.
Another question for you, Christian. This comes from Astrid. Great talk, by the way. I was also wondering, what other devices do you synchronize with?
Yeah, so obviously the customer device, that's the big one. Depending on what client we work with. That can be anything from a vehicle infotainment system, so we might read out CAN bus information. It could be an aftermarket device, a cell phone, or a GPS system that you put in the car, or really any type of device that a customer might introduce. And on top of that, we have a pretty complex environment in our simulator running. We have computers that run the simulation. We have computers that control all the functions of the vehicle. We might have additional logging devices, like I mentioned, biometrics. We could have pressure sensors on the steering wheel, for example, to record when hands are on the wheel and off the wheel. And so all of these things need to come together. And we've actually developed our own internal synchronization protocol that we run in our simulator that basically records these timestamps of our central computer, records the network delays, records the transmission delays, and records also the differences in timestamp throughout the recordings. And then in the end, we can bring that all back together and synchronize it to one timestamp.
Another question from Caroline. Can you simulate day versus night within the simulator? For example, ambient light as well as simulator conditions.
Yeah, absolutely. We use Virtual Test Drive, which is a commercial software for our simulator, and we have full control of the daytime, the weather conditions, so we can go anywhere from dusk to dawn to midnight. We can turn lights on and off. We can switch to rain. We have low light scenarios in which you get those glare effects onto the windscreen. Obviously, creating reflections is a little bit difficult because you need obviously a lot of sunlight to hit the windshields directly for those glare situations. But we can create that sensation of a bit of a blinding sun on the horizon. And all of that is completely controllable.
Next question comes from Natalie. This is for Mind. Do you offer any research services within Tobii Pro? Yes, great question, Natalie. So in terms of your research, whether it's automotive or whatever your application might be, we do have our own internal research team. It's called Tobii Pro Insight Research Services. And we can help with every aspect of the eye tracking projects, from project design to recruitment to analysis to reporting, or if you want, we can conduct the entire project customized for your research goals. So happy to send out more information on the team, as well as some really great case studies if you're interested after the call. The next question comes from Batel. Is it possible in your driving simulator to simulate level 3 and level 4 automation?
Yeah, absolutely. Again, as I mentioned, we have that comprehensive understanding of the surrounding, so we don't have to worry about sensor quality or actually having sensors that can detect vehicles around us. We have that knowledge, so we can pretty simply build a function that adheres to the surrounding, or that follows more or less the parameters that a client would give us for their function. And we've actually tested a couple of those aspects with the State University here in San Jose. We've done 2 studies with them on specifically vehicle disengagements of level 3 and level 4 automated systems. So those critical moments where the system says, I don't know what to do anymore, the driver has to take control back. And so we were able to simulate that automated function. And then the researchers from the university, they looked into how quickly can people take back control, what happens visually. They included eye tracking in that research as well. And anyone who's interested, you can shoot me a message. I can share those papers. They've been published, and I think both of those studies were actually put into a DOT report for the Department of Transport. So they're publicly available. I'm happy to share those.
I know we are at the top of the hour, so Christian and I will stay on for another 10 minutes or so answering questions, but for anyone who has to hop off, we will be sending out these presentation slides, the recording of the full session, and we'll be addressing any questions we don't get to during this live session after the presentation via email. Moving on, the next question for you, Christian, as well. This one comes from Jason. Can you automatically correlate driver gaze with an object within the simulator? For example, can you say, yes, the driver looked at this stop sign for this long at this moment in time? Does this require manual intervention, or is it truly automated?
We haven't done that. It would be interesting to see if we could automate it all the way. The absolute benefit is if you use the Tobii Labs software, you can go into that live view with the gaze overlay, and you can see if the participant looked at that specific object. It would be a little more tricky because if you wanted to automate it, you would have to have a time of interest and an area of interest on your snapshot, where you would have to very accurately capture this. I'd like to say if we put some time into it, it's probably possible. Again, because we have the benefit of designing the track and we have that full understanding of where the vehicle and the participant is at which time and which direction the car is pointing, and by that we could specify that area where he or she would have to look at which point in time, and by that we could probably automate it. It's just something we haven't done yet, but it sounds plausible. And then the automated gaze mapping, I've talked about that works pretty well. I would say we always like to check it back manually, but in more cases than not, we realize that we're not really helping it that much anymore. So with that, yeah, I think it would probably be possible to do that automatically.
This next question from Rachel looks like it applies to both of us. So I'll take the first part of the answer. Question is there a maximum amount of time that you recommend a participant wear the eye tracking glasses for scenarios? So in terms of, basic scenarios, automotive, usability with smartphones, wayfinding, those types of things, it really depends on what your overall application and what your research goals are. We've had tests where it's, 5 to 15 minutes, just a quick reporting session. We've had tests where it's an 8-hour, assembly line situation where they wear it during their entire shift. So it really depends. But the nice thing to point out is that with the glasses, there's that lightweight, that comfort factor. So you can have them on for a short amount of time, for a long amount of time. They're not going to block any of the visual field or create any discomfort for your participants. So you can kind of have that freedom based on what you're testing. But I also want to pass it to you, Christian. What has been your experience within your simulator with the glasses? What lengths of time have you tested with the wearables?
Yeah, I'd say the absolute maximum we've gone to was probably 2 hours. That includes all the paperwork and the screening questionnaires in the beginning. But that really gets people to sort of the limit when they start becoming a little disgruntled and unhappy after 2 hours of being very concentrated. And testing is usually for most participants a bit of a stressful environment, or at least something they're a little anxious, nervous, they don't know what to do, they want to do it right. So 2 hour I'd say is a maximum. Also with the eye tracking glasses, like Keith mentioned, you can plug those in, especially if you're in a vehicle where you have power outlets. Then that's not a problem. But I would say the sweet spot is probably an hour of actual having the participants on site. And we just recently finished a study where we've had the eye tracking run for maybe a total of 15 to 20 minutes in the drive. So yeah, kind of what you said, Keith. The bandwidth is pretty large, but you don't want to go too long generally.
Yeah. This is another two-part question for both of us, Christian. For both Keith and Christian, how are your companies handling COVID precautions with in-person testing? I can go first on this one. We've developed a COVID in-field response plan. It's a PDF document that I'm happy to send out to you and to anyone else who's interested after the call. But it's all in accordance with the CDC guidelines for COVID safety, and it goes over all the ways that you can that our researchers make sure that the equipment is sanitized and safe, that they're safe, that participants are safe, so the entire experience is in accordance and safe for everyone involved. So that's our approach, is we have a specific plan for in-field testing in place.
Yeah, it's pretty similar for us. It involves a lot of sanitization wipes. Every surface needs to be cleaned off between participants. Obviously, the eye tracking glasses are pretty good. You can take the nose pieces off, individually sanitize those, sanitize the frames and the recording unit. And we also handle it in sort of the most distant way. We already try to separate the participant as much from anyone as possible anyway, to not bias them and not to give them any cues or instructions to be potentially biased in the data. And now we take that to the next level where, you know, face shields and masks are mandatory for our instructors, but we try to keep those 6 feet distance or more at all times. We place them in the vehicle, instruct them from a distance. And then we use, while they're driving, we already, before COVID, we've always used sound cues to instruct them during their drives. So while they're actually testing, there's no one in the same room with them anyway. And so that makes it a little bit easier for us. But obviously we're taking that very seriously. And I think, you know, we'll probably have to continue doing that well into early next year, I believe.
This next question from Adam for you, Christian. How do you modify your simulator regarding the vehicle and vehicle interfaces? Do you swap vehicles in and out or reprogram the vehicle you have there?
We can do both. So our simulator is essentially vehicle agnostic. We can move that vehicle out and put a different one in. What's really important when you do that, you have to make sure it's immobile. So you don't want to have a car that isn't fully immobilized and all of a sudden you want to drive in the simulation, but you start driving in real life. But we've done that. There's different ways of setting that up. You can create additional mock-up vehicles that are stripped down versions that include that desired infotainment or interface that you're looking for. Another way that we've done in the past, and I think we've published this as well in a paper through our mother company in Germany, is we can set up a simulator that has a fully functional vehicle, and we basically prop up the wheels and tap into its input systems, and then you have the actual running vehicle, but we place it in an immobilized position in the simulator. So we could do that. The other way, yeah, the vehicle we have is completely customizable, both hardware and software. We've removed all the interior pieces that were displays that we couldn't access and replaced them with displays we can completely program. So we can display customer software, customer systems, but we can also just replace the hardware components if that needed to be done for a client.
This next question from Astrid for Keith. For the Pro Glasses 3, is it possible to record to an external storage device? That's a good question. So with Glasses 3, you can only record the data to the provided SD cards. So it does come with 3 32GB SD cards. Those slide into the side of that recording unit. It's clipped onto the person's pocket or belt, and that's where the data is directly stored. But it's not possible to just save it somewhere else. In real time, it's only possible to save it to those provided SD cards. Question for Christian from Batal. Christian, you mentioned about the looking but not seeing phenomenon. So is your system able to detect that when a person is doing that?
That's a good question. We don't detect that live, obviously, but we can get to it in the data processing afterwards if we record the right set of data, right? So as I mentioned, it's a phenomenon that occurs partially visually, but for example, in some of the videos you might have seen there was this red LED light flashing on the dashboard of our vehicle. That's actually part of another task that we give participants in certain cases. It's called the detection response task. And what you do, you either provide a visual or a tactile stimulus to a participant, not to see if they're, well, in the visual case, to see if they're visually loaded. With the tactile one, you want to see if they're cognitively loaded. And so if we see a participant is looking straight ahead, for example, but misses this detection, this stimulus that we present to them, then that's a really good indicator for us that they are cognitively so loaded that they might not be actually processing what they see. So you can't really get to it just with visual data. You have to have additional performance indicators that help you get to that. But yes, I mean, to the degree it's understood, we can get to it.
And it looks like we have one more question. This one's for you, Christian, from William. How many simulators do you operate and where are they located? Do you work with Detroit automakers as well?
Yeah, so we have the one static one here in San Jose. That's the one you see in my background. In addition to that, we operate a couple of simulators in Germany, static ones, and we also have access to the highly dynamic one that our corporation partner that we were founded out of the Institute for Automotive Engineering in Aachen, Germany, operates, which is this, this hexapod that moves. That's the full dynamic setup that you can see. We do work with Detroit. We're trying to serve all of North America. We don't have a presence there. We don't have a simulator there yet, but our experience is that a lot of the big automakers have their own setups. And then we just sometimes work with them to make sure that, we execute some of their testing externally. In some cases, that's just compliance ways. It's better to have someone external test something, or we just consult with them or work with them on finding the right way to test something.
Great. Well, I think that's the end of the Q&A. Looks like we're at time as well. For the questions we didn't quite get to, we'll make sure to email those answers directly. Christian, a huge thank you to you for joining today's session. I thought it went really well, and I appreciate your time and all the detailed information. Thank you to all of you who attended as well. We had about 62 people join at the height of the presentation, so appreciate everyone's time. We'll send out these slides and the recording shortly. Otherwise, have a great rest of your Tuesday. Thanks, everyone.
Thanks for having me, Keith. Thanks, everyone.
Thank you.